Hi everybody, in what may or may not become a series, Fun with Physics, we'll look at a couple of things in racing, F1 in this case, and see how the physics can be used in a fun way to make some predictions about what's going on, why it is going on, why it's not going on. And we're on the internet, so everything is theoretically, and despite it being the internet, I wouldn't say I'm always right. So flame on in the comments. I find it interesting and a bit sad that Honda is not really getting anywhere in F1 with McLaren for the third year now. You would sort of expect them to do better. And well, they just have a huge gap on the straight. The speed deficit is huge. So is there a way to calculate roughly what that means in power levels? Well, let's see. This is some stuff I got from the internet, so it's always perfectly correct. A couple of speed traps, and well, you can look at the numbers yourself. The average gap in top speed is about 16 kilometers an hour. And this is all a bit, has its tolerances with or without a toe, I don't know, with or without DRS, and there is some tolerance on it, but let's say 16 kilometers an hour is probably not a bad number to use as the speed deficit that they have. But what decides on your maximum speed? Well, it's almost completely down to the drag and the power. There are some other things, but a lot of them are the same whether you have a McLaren or a Mercedes, so a Honda or a Mercedes engined Formula 1 car. A couple of things that are the same are the rolling resistance from the tires. Well, everybody uses the same tires, so that's pretty much the same. And there are just some small things like losses and friction in the bearings or in the drivetrain. Now actually drivetrain losses, they might play a role, and perhaps Mercedes has better lubrication and more efficient drivetrain components there, but it's a fairly small part. So if you know the drag, so the wind resistance and the power of the engine, we can calculate the top speed. What is drag? Well, it's quite a drag. Something you cannot go without, sadly. To go twice as fast, you encounter 4 times the wind resistance. And if you go 4 times as fast, you get 16 times the wind resistance. So it becomes progressively harder to go faster because the wind resistance becomes incredibly strong at a certain point. Power then, how does that work? Well, the engine typically runs at an ideal RPM, say 10,000 RPM in Formula 1. And if you want to go faster, well, you can make more revs, but then the engine is no longer at its optimum, so you have to change the gearing. And if you change the gearing, so you change the gear so you go twice as fast, in order to go twice as fast, you lose half the torque, half the driving torque at the rear wheel. So that's what provides the forward force that pushes against this wind resistance. So if you go twice as fast, you get half the torque. Go 4 times as fast, you get a quarter of the torque. And go 8 times as fast, and you get 12.5% of the torque. So that's a linear relationship. These two things have to be combined then in a certain way. So drag resistance grows with speed squared to the second power. Torque is lost with speed just to the power of 1, so just linear with speed. And that means the total resistance has a third power effect, so that's really progressive, really exponential. The formula, as simple as it looks, power is drag times speed to the third power. Power. I've failed this Funet physics thing, but hey. With that in mind, with that stuff in mind, the equation, well, what is more fun than fun with physics in a PowerPoint presentation? Fun with spreadsheets, baby! So, on we go. Possibly Alt-tab, too many things open. There we are. So, here we have the spreadsheet with a summary of the stuff we discussed in, well, we didn't discuss anything. I was just talking to you and you had no chance to interrupt me or throw rotten fruit at me. Sorry about that. Perhaps a future version of YouTube will allow you to throw objects at the guy who's making the video. Not yet though, thankfully for me. So, what have we here? A table with a Mercedes and a worst case, medium case and a best case Honda. The maximum speed typically of the Mercedes engines Formula 1 cars is about 330 kilometers an hour. and we have to guess a drag coefficient, which I've done. I've guessed one, and doing the math, doing this formula gives us 930 horsepower required to do that 330 kilometers an hour. Fair enough? Possibly. We don't really know how much power they make. Now, I think they might make a lot more power than that, but in top gear, in 8th gear, I don't think they can use the MGUK or the curse system, you know, the fake electronics boring power to the fullest, because it would run out fairly quickly. At least that's what I think it happens. So they might have more than 1000 horsepower already when they run the maximum level of battery power added, but I think at top speed they won't have that. So a number, is it true or not? I don't know. Let's go with 930 horsepower for the Mercedes. Then we have a worst case, a medium case, and a best case for the Honda. Why these three cases? Typically, if you have an underpowered Formula 1 car, you will get passed on the straight. You don't want that, and one way to reduce the drag of your car is to run less downforce. And this of course has the penalty of losing some grip under the braking and grip in the corners, but at least on the straights you might go quicker. And we don't know if McLaren runs less drag than Mercedes engined cars do. It's likely. So the worst case would be if McLaren runs a lot less drag than Mercedes and still has this speed deficit. So let's say the worst case is 0.84, so they run quite a bit less drag than the Mercedes engine cars. Then we see that if you could get 314 kilometers an hour with this drag, it only requires 747 horsepower. So if they run less drag, so that's the worst case, so the making the Honda look the worst, it could be true, I don't know. There will be a 182 horsepower deficit gap to Mercedes. Okay, what about a medium case then? They have a bit less drag, but not as much. Would still result in a 155 horsepower gap to Mercedes. And the best case, I think it's the best case, they would have the same drag coefficient as the Mercedes. It would be strange, in my opinion, if they would run a higher downforce, higher drag setup than Mercedes, because that would only make them even slower on the straight. So I think the best case scenario is, at least to make Honda look the least worst, is to have them run an equal drag, equal amount of drag than Mercedes does. Even then, though, the gap to Mercedes is 129 horsepower. So 16 kilometers an hour top speed doesn't look like a lot, but because this third power element means that it takes a lot of power to gain 16 kilometers an hour. And looking at the medium case, it wouldn't be strange if Honda lacks about 150 horsepower in this case. Holy crap, that's a lot. Hopefully it's a bit less for them and it's more like this area, but I wouldn't be surprised if it's in this area, in this region of power. So that's a huge amount for Honda to make up, and I doubt they will pull it off this year. So anyway, guys, thanks for watching this first in a series of perhaps one, perhaps more videos about fun with physics and of course fun with spreadsheets. I wouldn't do it otherwise. Have a nice day, guys. Bye bye.